Hey everybody. I'm going to do an example. I had a request for an example of a kind of sum, kind of infinite sum that I don't think I talked explicitly about in any of the previous lectures, but it is in the section 11.2. So what this is something called a telescoping sum. So I was asked to do a couple of specific problems. I'm actually not going to do them, but I'm going to do the same type. So you still have a chance to try those in the homework. So let me share my workspace. The sum I want to do, let's take a look at this infinite sum. The sum from n equals 1 to infinity of 3 over n times n plus 1. Okay. So there are other ways we can get at this, but I'm gonna do the following. So I want to rewrite this sum first of all. So this is a little trick that sometimes proves useful with these kinds of things. So this expression for the terms. You might remember that you've worked out in previous classes how to separate these into two fractions using the method of partial fractions. Right? This method still works. Right? There's nothing wrong with it algebraically. I multiply both sides by the denominator here. I get 3 equals an plus a plus bn, or 3 equals a plus b times n plus a. This is a pretty straightforward one. I know that a plus b has to be 0 since n doesn't appear on the left, and then the constant a has to be equal to 3, which means b has to be equal to -3. Right. Which means this sum that we started with could be written as, it would be 3 over n minus 3 over n plus 1. Okay, so now, is this helpful? Well, let's look in particular at the following. Remember, infinite sums the definition of an infinite sum is it's equal to the limit of the partial sums, if those partial sums exist. So let's take a look at the partial sums. So remember, S1 is just going to be the sum from n equals 1 to 1 of our series. I'm just going to write a sub n for now, so I don't have to keep repeating this big expression. But if I put 1 into this expression, I get 3 over 1, or, yeah, let's just write it that way. 3 over 1 minus 3 over 2. Right. Now, we could simplify this. I'm going to leave it for a moment because sometimes it's nice to see what pattern is emerging. S2, the second partial sum, is n equals 1 to 2 of a sub n. So I get the same first term, right? This is my a1. And then I put in 2 for n, and I get plus 3 halves minus 3 over 3. Right, this is A2. Let's do one more. N equal 1 to 3. This is our third partial sum. So we still get the same first two terms. Then I put in n equals 3 into our expression, and I'm going to get plus 3 over 3 minus 3 over 4, right? So one thing we might notice is happening, right? These two numbers are opposite. And then here we get these two numbers are opposite, and these two numbers are opposite. Remember, right now with the partial sums, these are not infinite sums, so there's rules about we can't mix up terms and combine terms in certain ways. But we're not dealing for infinite sums, but we're not dealing with infinite sums right now. These are just partial sums. This is regular old addition, regular finite sums that we're adding up here. So what I'm noticing is that we always cancel out everything except for this first 3 and the very last term. In other words, let's write a general statement. The nth partial sum, let's call it the kth partial sum, since I'm using n to index here, up to some number k, well, I'll get all these same terms dot, 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 and I'll stop when I get up to 3 over k minus 3 over k plus 1, right? But this pattern tells me everything is going to cancel out, right? So I didn't write, there's a term right before this one that has a negative 3 over k that cancels this, and the only thing that's left is this, which means the kth partial sum will look like 3 over 1 or 3 minus 3 over k plus 1. Okay. Right? So as k gets larger and larger and larger, I don't actually have to keep adding all these terms because I see what's going to happen. Everything's just going to keep getting canceled out, and we're going to get 3 minus this expression. Right? Now remember, our infinite sum is equal to the limit of the partial sums. So let's just go now. I have a nice expression for the partial sums. S of k is equal to 3 minus 3 over k plus 1. Right? Or I've used n here, so the limit as n goes to infinity of 3 minus 3 over n plus 1. Well, what happens to this expression? The limit of the constant doesn't change. Nothing changes about 3 as n gets bigger and bigger, so that stays as a 3. And we're minusing 3 over n plus 1, which goes to 0. And so this sum is going to sum up, our infinite sum that we started with has a sum of 3. Okay, so this is what's called a telescoping series. And so the problems I was asked about have similar kinds of expressions. I know there was 2 of them. One of them was the partial fractions like this, so you'll have to find the partial fractions, right? Do your little partial fractions work and see if a pattern emerges that lets you write it in some nice way. The other one uses logarithms, which often have the same thing, where there's probably a division problem inside the logarithm, which lets you write it as 2 logarithms subtracted from each other. And you can find the same kind of cancellation. I know section 11.2 also has examples like this, so if you need more examples, they are in there. And that is it for this one. Thanks.